Thanks so much. Thanks for coming, everyone. So I'm going to kind of give a high-level introduction to Rust, kind of some of the very basic concepts behind it, it's kind of the underpinnings, and kind of hopefully give you a bit of a taste walking away, kind of why you might want to use Rust, how you might be able to use Rust, and kind of how you can benefit from it. This will be kind of interesting if you're here for the Idris talk, a very interesting contrast between the two, just to kind of fun to see all the new language development and all the language research nowadays. So first, let's talk about what Rust is. And if you take a look at our website, you'll see this soundbite saying that Rust is a systems programming language that runs blazingly fast, prevents nearly all segfaults, and guarantees thread safety. Those are some pretty lofty goals for this one language to be doing, and also claim that it's a systems language all at the same time. So I'm going to kind of break this down, and we'll kind of see as we go along how we can actually guarantee all these really nice properties. But first, let's take a look at the existing language landscape in the kind of the area of systems programming languages. We can typically graph it on these two axes of control versus safety. Where on one end, we've got C and C++. These languages are unfortunately very unsafe. They have a lot of memory safety problems. You can get memory corruption, use after freeze, double freeze, all these crazy things which cause things like heartbleed or cause various security vulnerabilities in like web browsers. But on the other hand, they give you this really high degree of control that's very hard to find elsewhere. And this allows you to write the fastest kind of program that you actually want. You have a very direct translation when you see C and C++ to what assembly is actually running, what's actually running on the machine itself. And that's why these are so popular nowadays. It's very tough to find other languages that actually enable you to do this. And that ends up meaning that these programs are called these languages are called the low-level languages. And that's kind of whenever you think low-level, you just automatically think of C and C++, and you kind of stop there. But as we move along here, we'll see kind of another group of languages somewhere in the middle. Things like Go or Java or Scala. And the defining feature of these languages are they have a very large garbage collector. And so this garbage collector is going to give you a much higher degree of safety than C and C++. You don't have to worry about use after freeze. You don't have to worry about memory corruption. It's entire class of bugs have all been erased. But on the other hand, this comes at a trade-off of control. A garbage collector now gives you these indeterminate GC pauses. You don't really quite know when your resources are going to be deallocated. They can kind of go away at any one point in time. So we're kind of moving down the level of control, but we're increasing safety at the same time. And if we go even farther, we'll see languages like Haskell. Haskell will give you a ton of safety. That's kind of the whole underpinnings of it. But on the other hand, Haskell is a very lazy language, so it's very difficult to actually reason about the runtimes. The level of control you're getting over what you would expect from C and C++ is much less. So what Rust is doing is it's kind of looking at this trend and saying, we can either trade off control versus safety, and let's just step off this entirely. Rust is giving us both the level of control that you would get from C and C++, but also the level of safety that you would expect from languages like Haskell and kind of other modern developments like that. And what this is essentially redefining is kind of when you think of low level today, you think of C and C++, and you're like, oh, those are unsafe. I'm not actually going to use those. I have to be a serious guru or wizard to actually be able to use that. And Rust is saying, we can actually reverse that a little bit. Rust itself is a very low-level language, but it's also safe. Low-level no longer just means, oh, I can't use it. This is too difficult for me. So Rust is kind of packaging all of these up in kind of one nice bundle for you to take a look at. So why would you might be interested in Rust? You may not always be interested in C++, but so with Rust, there are two big use cases of you're already doing systems programming. You're already hacking around in C and C++. But you don't really like having to worry about all these memory safety issues. You don't really like having to kind of constantly read bug reports, step through debuggers, have these crazy crashes, you don't really know what's going on. But so you want that level of safety, or you just want some more modern languages you would expect from a language, modern features from a language that was produced in about 2015 or 2016. But on the other hand, you might also be a very high-level developer. You're working in JavaScript or Ruby or Python, and you want this level of systems programming. You have these tight loops, and you want to run a lot faster, but you can't do that in your source language. So you need the control of C and C++, but you're very intimidated to actually go down to that level. So with Rust, you can kind of retain the safety contracts of your original language while also going down and enabling to have a much faster implementation that, like you would get in C and C++. The next thing you might be wondering is, why is Mozilla doing this? Why is Mozilla making a new programming language? And it turns out that Mozilla's flagship product, Firefox, is a browser, and browsers need a lot of control and a lot of safety. All browsers are incredibly competitive in terms of performance. So Firefox and Chrome and IE and Edge, those are like, you would choose your web browser basically based on speed nowadays. So they have to be written in C++ to get that level of performance to edge out everyone else. But at the same time, the browser is your gateway to the internet. It's just dealing with all this untrusted content constantly, and it has to keep you safe as you're browsing the internet. And that's traditionally very difficult to do with C and C++ because you have all these problems that come out just from very large millions of lines of code bases. So Rust is coming in saying, this is a language that can solve these problems. And you can actually see this envisioned in a new web browser coming out of Mozilla Research called Servo. And Servo is actually a reimagining of kind of rendering engines where it's not only writing a new engine in Rust, but it's also adding new concepts that are very, very difficult to implement in C++ today, the biggest one being parallelism. This is experimenting with parallel layout of web pages, which see massive performance improvements so far. But if you were to try and retrofit this on the existing engine called Gecko inside of Firefox, it would be multiple man-years of effort if you could even get it done. And even at that point, you would have no idea that it's actually safe because it's so difficult to understand all of the interactions between all of the C++ components. So Servo itself is kind of its own separate talk. I'll talk about that later if I can, but we'll just move on for now. So I'm going to kind of dive into what do I mean by control and what do I mean by safety. I'm talking about these things that Rust gives you, but I want to give you an idea of what's actually happening. So let's take a look at C++ where I kind of where there is a lot of control. And here's just a small function, makes a vector of strings on the stack. We do some stuff to it and get a pointer to it. So the first thing we'll notice is that this vector of strings is laid out inline on the stack. So vectors have a data pointer, a length, and a capacity, and those three variables are just sitting directly on the stack itself. And then this data pointer goes in the heap, and on the heap we'll notice that every element of that vector is just stored inline right next to one another. And it turns out that strings are typically just a vector of bytes internally, so if we kind of zoom in, we'll see that these elements of the array themselves have a data length and capacity pointer, which the data then points to a list of bytes on the edge. But the key thing here is everything is laid out in line. There's kind of no extra layers of indirection. You have very fine-grained control, and if you were to write this all by hand, you'd probably do it almost exactly like that. And the next thing we'll see in C++ are these lightweight references. This little pointer is actually just a raw pointer in memory pointing directly at the first element in the vector. And this is nice because there's no extra tracking metadata, there's no extra fluff around this. All it is just a pointer straight in memory, just this raw pointer sitting around. We'll see some problems with that, but it's very nice in terms of cost. It's very lightweight, it's very easy to work with. And the final thing that gives us a lot of control in C++ is this idea of deterministic destruction. We know that this vector of strings is owned by this example function. So as soon as this function returns, we know that we can deallocate it. We can free all the resources associated with it. We can destroy all the internal strings themselves. And that gives us a lot of power, actually, knowing when our resources are going to be deallocated. A lot of what these concepts boil down to are what we call zero-cost abstractions. And that's basically a fancy way of saying if you were to write this all by hand, you would do exactly what the compiler is already generating, which is that all this stuff you're writing just compiles down to nothing. The compiler will just rip through everything and tear it all away, and you'll be running at the lowest level that you would have done anyway if you were writing the assembly yourself. And as a counterexample to this, we can take a look at Java. So if we had the same vector of strings in Java, Java has this restriction where all the values are word size. So instead of our vector being these three pointers, we're actually going to have our vector being a pointer into some data, which then has the data pointer, and then all the elements of the vector itself are then another pointer, which is then pointing to more data. And we can see here there's extra layers of indirection going on here. This is not as compact as C++. If you wanted to write this as fast as possible, you probably wouldn't write this. And this is just, unfortunately, a limitation of the language itself. It's very difficult to overcome without actually going to another language or kind of dropping down to another level. And this zero-cost abstraction doesn't only apply to memory layout. This is also things like static dispatch and template expansion, where you want to know when you're actually writing some code and running it, is it going to be virtually dispatched? Are you going to be kind of running it directly? Are you going to be generating tons of code? Or are you going to be generating this little small amount that's very generic but a little bit slower at the cost of runtime? So having this control and having this knowledge of what's actually happening under the machine is kind of what these zero-cost abstractions are all about. So next thing is, let's take a look at the safety. So here we have our previous example of a vector of strings in the stack. We're going to take a pointer into it, but then we're going to kind of have a few problems that go along with it as well. So after we've taken this pointer, we're now going to push a new string onto this vector. Now those of you who have implemented vectors before know that if your vectors run out of space, you got to reallocate it, copy it around, and then add the new element onto it. So what this is going to do, or what it might do, is it'll allocate some new memory with a couple more slots. It'll copy over the existing data, in this case just the first string. It'll then add on a new string. But the key thing here is after we've done all that, we're going to deallocate our previous allocation. So this previous slot of just the first string is now gone. And we as the vector have now updated our data pointer because we're correctly tracking it. We're going to make sure it's all right. But as we can see here, we have this dangling pointer into freed memory. This is going to be a serious problem once we come around and try and print it. We're probably going to get some weird garbage to the console, or hopefully we'll get a segfault if we're lucky. But might be kind of difficult to debug, kind of depending on the situation we actually see this in. And it's kind of beneficial. That's kind of a contrived bug, and you'll see a lot of these in C and C++. And you can kind of situation solve many of these. But what we really want to do is look at the fundamental ingredients of what happened here. Why did this bug come up, and how can we prevent this just across the board entirely? And it turns out you can break this down into a few ingredients. The first one here we have is aliasing. So this data pointer and this element pointer that we had earlier will point to the same piece of memory. So these two pointers are aliasing, and we're going to have these problems once we try and update one of them, but we don't update the other. So after we have this aliasing, we then add in mutation, where one of these pointers are updated, we forgot to update the other one, and now we're going to have these serious problems. So it turns out these two concepts of aliasing plus mutation happening simultaneously is a source of a very large number of memory safety bugs in C and C++. And this not only kind of applies to just the bugs itself, but a lot of just idioms and kind of how you use the language. And once you have these two simultaneously, you'll run into some serious problems. So we'll probably kind of be seeing that a lot in the rest of the talk of what's happening once we have mutation and aliasing and kind of how Rust is helping you with this. And some of you might be thinking, okay, well, what about a garbage collector? This is exactly what garbage collectors are trying to solve. We have all this aliasing lying around. We can update some pointers. We know exactly how to do this. But garbage collectors come with some downsides. So as we were looking at earlier, garbage collectors give you less control than what you would expect. You have these indeterminate GC pauses. It's kind of tough to know when these things are going to go out of scope, so you don't know when resources are going to be deallocated. And then one thing you often forget when you think about a garbage collector is it requires a runtime. And this is a pretty serious thing sometimes. So if you take C and C++, which don't typically have garbage collectors, you can take a library written in them and kind of put them in any application. You can put a C library in your Ruby application and it'll work just fine. But you don't really often hear about taking your Ruby application and putting it inside of a Java application. And that's typically because the two garbage collectors are not going to play nicely with one another. So having this runtime, having to require runtime ends up being somewhat of a serious downside. But then not only this, but GC doesn't solve a lot of related problems. So if you've ever seen a concurrent modification exception in Java, this is the iterator invalidation problem. If you've ever seen a data race in C and C++, or just concurrency problems in Java, this is also a problem that garbage collection doesn't solve. And these are things that we in Rust are very, very interested in solving. And so our solution to this is not so much a garbage collector, but rather two concepts that we call ownership and borrowing. So these are the core fundamentals of Rust, which essentially everything else blossoms out of. And ownership and borrowing gives us these kind of really awesome properties of we don't need a runtime. This is purely a static analysis that happens at compile time, so it has no cost. It's completely zero cost. And this is the derivative source for all of our memory safety. You'll see, I'll kind of give you some examples of how these two are preventing these bugs we were seeing in C and C++. And then finally, we're getting this guarantee we don't actually have any data races. Rust is a language that doesn't have any data races in concurrent programming. That's a really, really powerful thing, and really actually kind of hard to find in other languages nowadays. So if we take a look at this, in C++, we have no need for runtime. That's kind of a great reason that you would use C++. It's embeddable, you can throw it anywhere, but you don't have this memory safety, you don't have this data race freedom. And with garbage collection, we have memory safety, but then we have a runtime, and we still don't get this data race freedom. So we can see how these concepts of ownership and borrowing are actually end up benefiting us quite a bit by giving all these benefits simultaneously. And in Rust, you'll also find a lot of other fun language features. So for example, you have pattern matching, which has been tried and true and proven in many other functional languages nowadays. You'll have smart pointers. So if you'll see this a lot in C++, where the standard library doesn't necessarily give you all the abstractions you want. So you can kind of build up your own and kind of have your own little thin shims around. And also stuff like, if you're familiar with Ruby and the bundler package manager, Rust comes with Cargo, a very similar concept, which gives you access to the entire ecosystem of Rust code essentially instantaneously. It's very easy to pull in other crates and start getting up and running very, very quickly. And all of this is suffices to say that Rust is a very modern language. It was released at 1.0 in 2015, and it has all the features you would expect from a language developed in 2015. So I want to kind of start diving into what I mean by ownership and what I mean by borrowing. I'm going to kind of give you a high-level view of what these are, how it applies in Rust, and then we'll also take a look at kind of how it actually enables us to give you this safety and concurrency, and we can eliminate all data races. So ownership basically just means kind of what the word actually means. I, as the owner of a resource, I own this book. I can then decide to kind of give this book to someone else. I pass ownership to them. I can then go away. That resource is fine. They own that. But once the owner of the resource goes away, we know this resource is not owned by anyone else. So this is the time where we can actually just destroy it. We can worry about it. We can deallocate everything. So I was talking earlier about how aliasing and mutation are these two simultaneous concepts that we have to prevent. Having these at the same time is the source of all of these, a lot of memory safety bugs in C and C++. So as with ownership, you'll see that we're going to be preventing aliasing. We're going to allow mutation through it, but we're preventing this one key ingredient to all these bugs. And so looking at this in Rust, we'll have a simple example where we're just going to make a vector on the stack. We're going to push some elements onto it and then pass it over somewhere else. So you notice immediately that, like in C++, Rust is storing this vector directly on the stack. We've got the data length and capacity pointers just stored directly inline. We're going to push some data onto it, so we'll push a 1, then we'll come around and we'll push a 2. Again, we'll see this is right next to inline. There's no extra layers of indirection here. This is kind of that zero-cost abstraction in play. And then we'll come along to actually calling this function where we're going to pass ownership of this vector. And the way we know that, when we take a look at this type signature, we'll see that this vec, just this bare vec of integers, that indicates that this function is taking ownership. It's going to consume it from the caller, and it's going to have access to it internally. And what that actually means at runtime is we're going to create a shallow copy of this vector. So we're going to copy this data length and capacity pointer to pass to the take function so we can have access to it. But as you can see, there's some aliasing going on here. So the key aspect of this is that the give function is going to forget its own copy. It's going to say, I no longer have access to it. All of the ownership of this data has now passed off to take. So take is going to start running. It can kind of do whatever it wants to the vector. And by the time it gets to the end, we know from ownership that this is the only place where you can actually access the vector. So it's time to deallocate, free the resources, make it all go away. And then we can come along back to the function give and run along our merry way. So you might be thinking, all right, that's all fine and dandy, but what happens if we actually try and use this vector after we pass take? Like we're running some extra code here, what if we accidentally try to use this freed memory? So for example, what if we just tried to push some more data onto it after it was freed after it? And what the compiler is going to tell you is like, no, this vector has been moved at this point. The function called a take was where you move the vector to the function call, to the actual function take, and so it's been deallocated after that. So this is going to be disallowed as compiler error. You can't use anything after you have moved it out to someone else unless they kind of give you back ownership. And what this ends up meaning is that we can prevent these entire classes of bugs you see in C++, like use after freeze or double moves or anything related to all of this. So this is kind of, with this one simple concept of ownership, completely eliminating these entire classes of bugs. So the next thing to talk about is borrowing. This is the kind of the duality of ownership, where if you have this kind of ownership system where you're passing around values, it's pretty unwieldy. What if I want to just kind of loan it out to you for a certain period of time? I don't want you to I don't want to pass it to you and then have you pass it back to me and I somehow shuffle all that state. So this concept of borrowing is kind of just, I'm going to allow you to use this for a small period of time. And in Rust, we have two kinds of borrows. The first of which we call a shared borrow. In this case, I, as the owner of a resource, I can take out a shared borrow, and then I can also take that shared borrow and pass it to a couple other users at the same time. These could be threads or function calls or data structures or whatever you like. But the key thing is you can have multiple shared borrows at once, implied by the name share. So again, these two ingredients of aliasing and mutation, we've seen that with shared borrows, we're going to have aliasing, so we're going to disallow mutation through shared borrows. But that wouldn't be very good if you can't actually mutate things through borrows. So our second kind of borrow that we have in Rust is called a mutable borrow. And a mutable borrow happens when the owner of a resource decides to loan out a mutable borrow. You can hand it out one at a time, and then I, as the owner of a current mutable borrow, could then decide to pass it along to someone else. This kind of travels down the stack, and then once everyone starts returning ownership of this resource, still retains with the original owner. So this mutable borrow is passing on back up the stack, and eventually it's going to come back to the original owner, and they'll own the data again. So these two ingredients of aliasing and mutation, we've seen that mutable borrows are going to allow mutation, so we're going to be disallowing aliasing from these mutable borrows. So take a look at an example of what's going on here. Well, this is the same example from before where we create a vector, push some data onto it, and pass it off. So we'll have the same situation where we have a vector, 2 data points on it, but the difference happens when we actually call this function. this little ampersand sigil in front of the vector means that this is a shared reference to a vector of integers. And then this little ampersand sigil at the call site means that I'm taking a loan out on this vector temporarily. And what that's saying is, like before when we just saw the word vec, I'm not actually passing ownership of this. I'm only passing a temporary borrow for the actual function call. And at runtime, what this is kind of what you would expect from C++, is that this vec argument in the use function is just a raw pointer on the stack. It's just pointing directly on the stack. It's just this lightweight reference. There's no extra metadata tracking going on here, just a random pointer in memory. So this function use is going to run. It's going to go along its merry way. And once we're done, we're just going to forget about that vec pointer because now it's fallen out of scope and we no longer have to worry about it. And once we've come back to Lender, we can actually continue using the vector because we haven't relinquished ownership to it. We can then mutate it. We could add more things onto it. We could send out a borrow to someone else. And as I was saying earlier, with shared borrows, you can't mutate through this. So for example, the use function we saw earlier, you can't push some more elements onto it. You can't modify existing elements. These are both going to be disallowed by the compiler. And the summary of that is basically that a shared reference is almost always read-only. There's some caveats here where we do actually allow some mutation in controlled circumstances, and we'll see some examples of that a little bit later in the talk. But this is it suffices to say that when you see a shared reference, you can think immutable, and it's only read-only at that point. Let's go. Immutable references are also pretty interesting. So here's just a simple function where we're going to take a bunch of items from one vector and just push them onto another vector. So we have our from and our to. And this little ampersand mute is what means that this is a mutable reference to a vector of integers and how it's going to push things on. And because we have this mutable reference, we're actually going to be able to push unlike we could before with this shared reference. So taking a look at the runtime of this, we have our from pointer, which is going to have the elements 1, 2, and 3, and we're going to assume our two vectors empty just so far. So we're going to try and push this 1, 2, and 3 on there. So we're going to start up our for loop. And this is the way that elements actually working is it's just a raw pointer in memory, again, to just the 1, 2, 3 elements of the from loop itself. So like before, this is just a raw pointer, no extra metadata tracking it. It's just a thin reference to that. So the first thing we're going to do is push the 1 onto the 2 vector. We'll kind of turn the loop again. And the key thing that's going to happen here is this is just a very simple iterator over the vector. So it's a pretty simple operation we do now. Just a little pointer arithmetic. All we do is swing this pointer from the first element down to the second element, and then push that and keep on going with the loop until we push everything. Now, some of you who might have seen this before or kind of implemented some of this in C and C++ might say, what if these two vectors are the same thing? What if the from vector and the to vector actually reference the same underlying vector? So like we saw on the first slide, once we push an element, we might have to reallocate the vector and copy it out elsewhere in memory. So let's say this push operation where we're trying to push 1 onto the same vector does exactly that. So we copy over our 1, 2, and 3 over to the new vector. We push 1 onto it, but we've deallocated the previous contents. Now the bad part's going to happen here once we try and turn the loop again. We're going to swing this element pointer down to the second element, but that's now a dangling pointer in free memory. We no longer have any access to that memory. It's been deallocated. It's in use by someone else. This is essentially a segfault. So we take a look at how this might actually happen in Rust. This is our push all function from before, just pushing from onto to, and this is how we might try and call it. We'll create a vector, and then we'll try and actually call the push all function itself. And then what the compiler sees here is, okay, first thing I'm going to do is take out a shared reference. And I, as the compiler, know that this shared reference has to last for the duration of the push all function. So I have to kind of keep it alive for this entire time. So by the time we come around to this mutable reference, the compiler says, okay, well, I can't have both a shared and a mutable reference at the same time, so that's going to be disallowed. So if you remember, a shared reference allows aliasing but disallows mutation. And a mutable reference allows mutation but disallows aliasing. And exactly what we're trying to prevent is both of those happening at the same time. So we can't allow both references at the same time. So this is going to be rejected by the compiler. And it ends up having a pretty nice property of mutable pointers where this means that if you have ampersand mute t, that's the only way to access the memory it points at. You're guaranteed that no one else is concurrently accessing this, and it's not stored in any data structure, it's not kind of off in the weeds somewhere. You have the only way to access that piece of memory. And this ends up being a really powerful property, not only in terms of what the compiler can do in terms of optimizations, but also in terms of how you can reason about code. How you can understand, if I have an ampersand mute t, what can I do with it? Or if I'm handing off one, kind of what powers am I lending this function that I'm calling to actually be able to do with that memory? So this might seem kind of weird, like, okay, I can have shared references, and mutable references, but I can't have them at the same time. How am I going to juggle this all? I'm going to have all these weird annotations everywhere. But it turns out that Rust also has this concept of lifetimes, where it's kind of keeping track of the length of these borrows over time. So in this example, we create a vector, we're going to iterate over it, take a reference, and try and mutate it. But clearly this is very bad because we can't have a reference while we then mutate it at the same time. And the way Rust understands this is once we try and do the push, we know that this original borrow from the vec of I is alive for the entire scope of this for loop. So this element pointer is kind of alive during that entire scope, so we know that the borrow is active for that entire scope. And then while that borrow is active, you can't take out a mutable reference, so this is going to be disallowed. The compiler says that the vector is already borrowed for this period of time, so I can't allow any other borrows during this time. But on the other hand, it understands that once you come out of the for loop, you've exited out of that scope, and you can actually now take a mutable reference again. So you're allowed to kind of, once all references have gone out of scope, you can then continue to take more references or more borrows out on an element. All right, so that's kind of borrowing and ownership in a nutshell, kind of how Rust does that, how Rust uses it, and how you might be able to use it internally. So let's take a look at exactly what happens when we try and apply this to concurrency and how we can solve this data race problem we saw earlier. And Rust actually has a pretty interesting concurrency story over time. In the ye olden days, we only had message passing. That was the only, we figured that's a pretty simple way to reason about concurrency, and we'll just kind of have that, and that'll suffice for everyone. But over time, as a systems programming language, we ended up realizing that we actually need to, there are many other paradigms for sharing memory with concurrency as well. For example, there are locks, there are atomically reference counted pointers, there's all these fancy things. And we as a standard library decided to start providing them, and we can do this in a way using ownership and borrowing where it has the same guarantees as channels and message passing, which is that there are no data races, there are very few bugs, you can really avoid almost all footguns just by using these types and the safe APIs that they provide. So we'll kind of explore some of the paradigms and foundational building blocks of the concurrency primitives in Rust next. First of which, though, let's talk about these data races problems. I've been saying this word data race, and some of you may not be super familiar with it. And data race is actually defined in the C11 memory model, which Rust is also following, as two unsynchronized threads accessing the same data where at least one writes. That's kind of a fancy way of saying you have a bunch of unsynchronized access. Threads don't really know that they're sharing memory, and then bad things happen. And the problem with a data race is that this is undefined behavior. When this happens, demons fly out your nose, according to the standard, I think. There's some weird comment somewhere about that. But this is unsafety. This is exactly what we need to prevent in Rust. But if you kind of play that again, we'll say two threads, that's aliasing. At least one's a write, that's mutation. And unsynchronized, that's just a fancy thing for saying there's not a lot of ordering. That's just atomic stuff to worry about that. But that probably sounds pretty familiar by this point. This problem of aliasing and mutation is also what Rust is trying to do in a lot of other aspects. So if we can just prevent these two things from happening simultaneously, we're missing one of the key ingredients for a data race. So we've actually already prevented data races. We don't really do a whole lot. We've already solved all that problem. And what this really means is that if you don't have, by not having any data races in Rust, you don't have any accidentally shared state. There's no way to have state cross a thread accidentally. You didn't really intend for that to happen. You can only have to explicitly share state. And this also means that you can see code like this in C and C++ sometimes, but you can't always optimize this. That kind of looks trivially like, oh yeah, sure, you can optimize that check away. But in C and C++, there might be concurrent access to this variable. You don't have information about this pointer of what's actually happening. But in Rust, we know that these shared references and these mutable references, they're never accidentally shared across threads. There's no data races. So we have a lot of optimization benefits from knowing there are no data races as well by saying checks like this are always true. You can reorder writes, you can reorder stores, and that in turn is very important for various optimizations like vectorizing and fancy stuff like that. So let's dive into kind of how messaging and message passing end up manifesting themselves in Rust. And if you're not familiar with messaging or message passing, it's pretty much just I is the owner of message, another thread comes along, I can then send messages to them, and then you can also tend to send messages back and resources back. So this is mostly going to highlight how ownership is used in Rust to kind of encapsulate the best practices of a messaging protocol. So let's take a look at an example. We have this parent function where the first thing it's do is going to create a channel. This is just a function in the standard library. And what that's going to do is it's going to create a transmission endpoint and a receiving endpoint. And this is where you're going to send messages on the transmission endpoint and then receive them on the receiving end. And this might seem kind of weird as to when I created one channel, why am I actually getting out two things? And this is actually pretty cool in the sense that once we actually come down and we try and spawn this thread, the child's going to need access to some handle in this channel. It's going to have to send messages on something. So in this case, what this closure here is actually going to look like is something like this. And the key thing here is this transmission endpoint is captured by the child. This transmission endpoint is owned there. But if we still want the parent to actually still have access to the messages, it's got to call on something. So the child has now owned moved, or TX has now moved into the child, but we still have to, and by having this RX, this other half of the channel, we can still have some ownership on the parent itself, which can then pull messages out. That's kind of just a fun thing about Rust. So this transmission endpoint is going to move over to the child. The parent now forgets about it because it's been moved out, like we've seen before. Child's going to run for a little bit. It's going to create a vector, put some data onto it. Say, oh, we've seen kind of this stuff before. And what's going to happen when we actually try and send the message is pretty much the same standard thing we've seen with other moves, which is that we'll create a shallow copy, move it onto the channel. Child's going to forget about it, not going to worry about it anymore. And then once the parent comes along and says, all right, I'm now ready to receive this message, we'll take the data off the channel, move it over to the parent, and now the parent owns this data. So one cool thing here is that we saw that there's a shallow copy going on here of just the data length and capacity, but the actual contents of the channel or the vector were never actually copied. This always stays at the same place in memory. So this is actually a very efficient way to send over like very large blocks, like megabytes of data at a time. All right, so the next thing I want to talk about is another thing you might have ever done in concurrent programming, which is just blocks, mutexes. This is a pretty common way. You just have a piece of data which is protected by some synchronization primitive where everyone trying to access it just blocks until someone else isn't accessing it, and then you have exclusive access to it. So the way this looks in Rust, it looks a little bit like this. We have a function that takes a mutex, we're going to lock it, and then we're going to increment some data inside of it. This looks pretty innocuous, but there's actually a lot of stuff going on here, and it's actually pretty important as well. So first, we can take a look at this ampersand mutex of I32. So there's a couple primary things here. One, this is a shared borrow. So like we saw earlier, a shared borrow implies aliasing. So this is essentially saying this mutex might be referenced on other threads at this point right now. We don't actually have that much knowledge about it, so we have to assume there are other threads that are using this. But the second thing is this I32 is a type parameter on this mutex, which is saying that this data is actually owned by the mutex itself. And that itself is very powerful in the sense that it's like clearly worst practice to access data inside of a mutex without locking it. It's only ever safe if you block the mutex and then access it. So what the mutex is doing is it actually consumed ownership of this integer once it was created. And then from that point on, because it knows that it's the only owner and the only reference to that data, it can then control how it hands out references. So you can only access this data through the mutex itself. And the way we do that is first we create this little data sentinel, which is kind of a type that's not actually a pointer in the mutex, but it's a kind of placeholder value where the destructor is going to release the lock in a second. But the key thing is you can only access the data through the sentinel value. You can't access it into the mutex at all. So it's encompassing this best practice or the correct practice of you only access the data in mutex after you've locked it. Once we've locked it, we have mutable access to it because we know there's no other threads aliasing this because everyone else just has the mutex, not the contents. And then also, we're the only alias of this, so we have mutable access to it. And once we come out, because we have this deterministic control, we have this determinism like we have in C and C++, this data pointer falls out of scope, and then it'll release the lock, so you never have to actually unlock locks in Rust. You just kind of let things fall out of scope, and it just kind of naturally happens. And so the next thing I want to talk about is this pretty cool thing called disjoint scoped access. This is kind of a fancy way of saying that you can have a lot of parallelism, which is all stack-based, where you can kind of reference stack data, and it's really convenient. So I'll go through this with an example of the quicksort function. So those of you who aren't very familiar with quicksort, I always have to remember this all the time. But it's pretty simple. All you do is you take a random pivot in the vector, and then from this pivot element, everything less than the pivot, you move on one side. Everything bigger than the pivot, you move on the other side, and then you recurse on that. So this is just saying, take a random pivot, partition that vector by moving greater on the left, bigger on the right. We'll then split it into two vectors, and then we'll go and sort both these sides. But this is actually a pretty cool operation going on here, this whole split at mute function. This is saying we're taking a big window, we are now relinquishing ownership of it, and we're getting two smaller windows. So this is actually a lot of stuff going on here in terms of ownership and borrowing. So if we take a look at what split at mute is in the standard library, this function signature is saying it's taking a mutable reference to a slice, a point to split it at, and then returning two other mutable references. So we can see ownership at play here in the sense that it's consuming the first mutable reference. This first mutable reference is not going to be accessed again, so we know that we have the only unique reference, so we can kind of control access to it at that point. But borrowings also happen here where this fancy thing called lifetimes, where the lifetime on this first mutable borrow is now the same as the return two slices here. So we know that if we have a slice that's valid for a certain lifetime, if we kind of split it up and return subviews into it, they're also valid for that same lifetime. So we can kind of see both of those at play in this very simple function of just splitting a vector in kind of two separate halves. So it's kind of more fun to do this in parallel, so let's just make a parallel quicksort function. And this looks pretty similar to the previous one. We're kind of resuming where we left off. But right after that, instead of just doing it sequentially, we're just going to have this called this made-up parallel join API. And all this is really doing behind the scenes is it's going to run these two closures, the quicksort of the left and the quicksort of the right in parallel, and then it's going to join on the two results and then return once they both returned, or return once they've both completed. So that is kind of interesting, where we have this vector. We don't know how long it's alive for. We now have this slice in the stack. It's with the same lifetime as before, and now we're running and processing this in parallel on two different threads. That's interesting. So this is actually safe. This is safe to do, and the reason that this is safe is because we can actually be sure that once these two closures have returned, there are no outstanding references to the stack data. So we can safely say that we can execute this in parallel, these two disjoint slices, because and we still have mutable access to them. We can pass it off to multiple threads. This is kind of isn't actually an existing API in the standard library just yet. There's kind of some extra stuff bolted on to actually implement this in the ecosystem. But this is an example of how in Rust you can kind of use these primitives and you can use these guarantees of ownership and borrowing, immutable borrows, and what they all have access to. And you can implement a parallel quicksort essentially instantaneously with almost no effort. And one final thing I want to talk about in terms of Rust's concurrency story is that channels are all. This is taking a look at this send function for channels in the standard library, and they're all parameterized with this type of message that's actually flowing across the channel itself. And you'll see this interesting trait called send. This is the send bound on messages. And what this is essentially saying is that only sendable types can be sent across threads. That's kind of a fancy way of saying basically what these two examples are here, which is that arc is an atomic reference counted pointer. That's totally safe to send across threads. Any updates to the reference count are done atomically, so it's fine to happen concurrently, so we can send it anywhere we like. But RC, on the other hand, which stands for reference counted pointer, cannot be sent to other threads. You can't update the reference count non-atomically on multiple threads. That's a data race, which then leads to undefined behavior. And this is actually pretty cool, because if you've ever used C++ before, you've probably seen shared pointer. And that's very similar to arc here, where the updates to the reference count are all atomic. But the problem is you don't always send your shared pointers to other threads, and atomic updates are pretty slow compared to non-atomic updates. So in Rust, it's giving you the ability to control whether you want to send these to other threads or whether you don't want to send this to other threads. So you can kind of trade off the performance or whatever is suitable for the application at hand. But at the same time, if you choose the faster one, which is less featureful, it will also guarantee you don't accidentally send that to another thread. It will guarantee you don't actually have any data races by leaking that to someone else. And so there's a lot. This is not the full concurrency story in Rust. Concurrency is an area of very active development in Rust. There's tons of things going on in the ecosystem. We have a lot of crates like Rayon and Crossbeam, which are exploring new kind of GC-ish schemes for garbage collection in concurrent situations. Also, parallelism, like the parallel join API I was showing, is actually implemented in kind of in scope threads in Rayon itself. And we have this whole long list of things that we would like to do in Rust as well, and these are all enabled by the traits and bounds and guarantees that Rust is giving so far. And the key thing to remember from all of this is that everything you see here is always going to be data race free. This is this guarantee you don't actually get from C and C++ or many of the languages, where it's saying that you can have all this concurrent programming, and you can do it all very confidently. You don't really have to worry about all of these extra weird things going on. You can kind of use ownership in Rust to leverage all that fact to prevent all these bugs at compile time. So all of this seems kind of nice, but how are we actually implementing any of this? Channels themselves are all in the standard library. The Mutexes are in the standard library. All of Rust is actually written in Rust. So some of these were kind of bending some of the rules we saw earlier about ownership and borrowing. And what Rust has to solve that is this unsafe concept, this concept of unsafe code. And in Rust, that ends up coming out is safe abstractions. And you can do this so you can enter the unsafe code of Rust by having an unsafe block where you're basically telling the compiler, trust me, I got this. I'm going to take care of any invariants you want, any invariants you have. I will make sure that they are true at the end because you made sure they were true at the beginning. And this allows you to kind of bend the mutation and aliasing rules. So for example, the split at mute function, we can't implement that. Given one mutable slice, we can't really split that up into two. Like we, as the implementers, know that the two we're going to return are disjoint, so it is safe. But the compiler won't understand that that slice is actually, those two subslices are disjoint. So we have to rely on unsafe code to actually implement this. And then also, whenever you touch C, call out to FFI, call out to other libraries, we assume those are entirely unsafe because they could essentially change the world in any way, shape, or form. So you have to use unsafe code when interfacing with C. But the key thing in Rust is that you don't ever actually write this that often. When you're writing your big application, you're pretty rarely relying on unsafe code. And the reason for that is we have this safe boundary to Rust. We say that we have our safe function, which might do some input validation. It might kind of do some verification. And then it'll actually go and run this unsafe code, which isn't allowed elsewhere. And so an example of these safe abstractions is this mutex I was showing earlier. This mutex was a shared reference, which I said at the beginning was essentially immutable. You can't actually mutate through it, but then we were locking it and actually mutating through it. So that's kind of an example of bending these aliasing rules as well and kind of bending this mutation where it's still safe. Like mutexes are a safe paradigm in Rust, but you can kind of use unsafe internally to implement that. And then the API you export is all totally safe. So there's no actually unsafe way to use the mutex itself. All right, so to kind of wrap up here, I want to talk about also not just the technical aspects of Rust are pretty awesome, but also the community itself. And community has been a major factor of Rust long since before 1.0 as well. If you take a look at, this is one of my favorite quotes, as the Rust community seems to be populated by entirely human beings. And this is actually pretty telling, and it boils down to, if you take a look at before 1.0, we had over 1,000 contributors. And it's this incredibly welcoming and supportive culture where if you come into Rust, kind of come in the Rust channels, questions will be answered almost instantaneously. Any sort of changes or PRs to Rust are very welcome. Tons of review happens on them. The community is very supportive. And all this interaction, it surprises some people that, oh my God, people are actually here and people care and people are actually looking at this kind of stuff. But at the same time, there's always this notion of keeping it a little bit down to earth, making sure everything is practical, making sure everything is usable. I can actually use this in my everyday job or in terms of ergonomics, in terms of actually shipping this and all the weird, funny details that come up inevitably. And for that reason, Rust has always been developed in the open. Before 1.0, we actually instituted an RFC process, which is where anyone can propose any change to the language, the compiler, the standard library, all the major products of Rust today. And this is not only followed by the community, but also the core team itself. And the core team has tons of back and forth on RFCs as well, and everyone, and tons of iteration over what's actually happening. But through all of this, there's always a clear leadership of Rust itself. The core team has a very large mix of backgrounds on it to kind of ensure that the language has a very healthy upbringing in terms of diversity of what's actually happening. And we're essentially keepers of the vision. We essentially make sure that Rust is always going towards a kind of unified vision, and we help steer the community and RFCs and entire process towards this vision to ensure we're all working towards the same shared goal. And some examples of RFCs that we've seen are, this is an RFC for a new language feature which has tons of comments, tons of iteration that happened over it, tons of changes that happened over time, but it always came out for the best. Like this was something that I think, I remember talking about this and designing it a long time ago, and then by the time we actually got to the end of the RFC process, it was almost totally indistinguishable from where we had started, which for the better, because we get all these points of view and all these opinions we just couldn't even fathom to think about beforehand, until we actually came to the community and said, hey, everyone, like, what do y'all think of this? And it not only ranges in the RFCs in terms of language features as well, but also pretty complicated internals of the compiler. This is something that I don't actually myself really understand that much. And this is kind of a subsection of the RFC, which I also really don't understand that much. There's a lot of crazy stuff going on here. But we have an entire section of the community which is also working on this. If you see, this also has tons of comments, and our community is certainly very broad in terms of interests, and you'll see lots of different points of view and aspects looking into this. So to wrap up, what Rust is essentially doing is kind of giving you these really nice guarantees, which are very difficult to find in other languages. So Rust is giving you memory safety without garbage collection. It's giving you this control without sacrificing on safety at the same time. It's giving you concurrency without data races. So all these things you were afraid to do it before or retrofit onto existing code bases, you can do it any time in Rust because you can safely say if it doesn't compile, it's not going to work, and if it compiles, it's probably going to work. It gives you abstraction without overhead, which is the same level of control that C and C++ gives you. It allows you to go straight down the machine. You know exactly what's running. You can actually look at Rust code as well and reason about, oh, this is probably the assembly instructions that are running. This is how I'm going to vectorize this loop. All these crazy optimizations you do in C and C++, you can still do in Rust. And then finally, it's also giving you stability without stagnation. We have this massive community which has been pushing Rust since 1.0. And if you take a look at the difference between Rust 1.0 and 1.9 that was released a couple weeks ago, it's massive. We have tons of new features in the standard, new APIs in the standard library. We have a huge ecosystem growing in terms of new crates being developed, new features in Cargo, our package manager. It's very much making very steady progress ever since 1.0 because of this massive community push behind it. And the TLDR of all this essentially, and kind of Rust in general, is that you can hack without fear. You can just work in Rust and just stop worrying about all these random segfaults and debugging and weird sessions in Rust or in various other languages that you have. That's all I have for today. Thanks for coming. Any questions?
Why is locking a mutex not a mutable operation? If you pass it as a reference and not as a mutable reference.
Right. So that's actually one thing that I also like to talk about as well. Let me see what that slide was. Yes, this one. So if I had a mutable reference, remember a mutable reference, if you have it, is the only way to access that data. So if you have a mutable reference to a mutex, like ampersand mute mutex, no one else can have an access to that mutex. You're the only one with a pointer to that mutex, in which case locking actually doesn't make sense because you already have mutable access, so you can actually just go straight in there and grab the data. So the shared way is saying, the shared reference is saying that like this is safe to share among many threads. You can have references among many threads, and because you don't actually know if there are, at runtime, you have to go and acquire the lock. Does that make sense?
So when defining methods on structs, you can always choose if you take self as mutable or as immutable. So this is why the compiler allows you to do this.
Okay.
Yes.
What about deadlocks? If you have two mutexes, two functions, locking them in the wrong order?
Right. We've actually had, in long ago in Rust, we actually attempted to prevent deadlocks. Turns out it's kind of hard. So preventing deadlocks isn't actually a requirement for memory safety. It's more like if your program never terminates, well, it's still never going to segfault. So we actually do, we do nothing in terms of that. You can write concurrent programs that are certainly wrong, but they'll never have data races. They'll never segfault. It's just they might deadlock. They might have like weird results. It's just weird defined results.
How can this split vector back? Because you have split it into all smaller parts, but I have never seen it come back as a whole again.
Right. That's actually a pretty cool thing to do. So here we have this less than greater. If we forget about less than greater, we now have the original vector as well. So there's no actual fuse operation to say take these two slices and give them back. It's actually more you forget about the slices and then you have the original slice back as well. And this happens because all you're doing is this original slice, when you borrow it, you're actually taking a lifetime loan out on it. So like during that lifetime of which you borrowed it, you can only access those two slices, not the original one. But once that lifetime expires, you can come back to the original slice itself. So if you think about it, internally, the kind of recursive step here is going to split this left and right-hand side. But once we come back to the top, we still have access to less because we still have access to the outer vector. So it's kind of, in essence, being assembled back together.
It's not in place.
In terms of?
Sorting is done in place.
Yes.
That's why we don't join pieces together in the end.
Right. Yes.
Yes, your compiler is doing a lot of work, so how are the compile times?
That is a very good question. The answer is not so good. So if you take a look at the analysis of compile times in Rust is something that we are very much aware of and very much working to improve. And the biggest thing here is actually almost 90% of our time in terms of compile time is translating to LLVM. LLVM is our backend, which is just the same backend for like C++ and Clang, and then also in optimizations. So that's kind of the major slowdown is actually just generating all this code and optimizing all this code. And so we're looking at a couple things. We're doing a massive compiler refactoring now to just plumb through a new IR ourselves, where it's going to make translation times much, much faster. And then also we can enable optimizations on our own in our own compiler. Currently we do no optimizations, but eventually once we do that, we might be generating less code. And then the other major feature is we're adding incremental compilation soon, which is that currently the unit of compilation in Rust is much, much larger than in C++. So you feel the pain of this compile time very iteratively over time. But what's going to happen is this, once we have this incremental compilation, the unit of incrementality is going to be much, much smaller. So the actual work you have to redo whenever you kind of modify something and recompile it to see if it works is much, much smaller. So a lot of improvements are coming here soon. But in general, the compile times tend to be better than C++ in terms of one absolute compile. Any benchmark I've ever seen from a similar C++ project to a similar Rust project compiles in essentially the same amount of time, where Rust is almost always a little bit faster, if not way faster. It's just this iterative process of kind of modifying a little bit. In C++, you have to recompile very little, where in Rust you have to recompile a lot. But that'll be fixed with incremental compilation.
But you're not in the regions of O or something?
No. We're not going to get 5-second compiles anytime soon. I was actually looking at the D standard library compiles in like 10 or 15 seconds. Our standard library compiles in like 2 or 3 minutes. Made me very sad. There's a question over here.
How do you deal with integer overflows? Because this is also a source of issues.
Right.
How do you deal with them?
This was actually, I think, our most commented on RFC was implementing integer overflows. And the way that we deal with it in Rust are there's kind of two modes. We have debug assertions in debug mode, which trap on integer overflows. They panic in Rust, which is just kind of a way of saying, kind of throwing an exception, more like, it's kind of complicated. But essentially, we catch overflows in debug mode, and we throw an exception, and you kind of explicitly opt in saying, this operation right here in my random number generator is an overflowing operation, so make sure we do that. And then in release mode, it was concluded that integer overflows today are currently not performant enough, so you would sacrifice too much performance to have an overflow checks in release mode, so by default, they're turned off. You can turn them on, though. And once you have them turned on in release mode, they are defined as two's complement. So they're not undefined behavior, like it's totally fine to happen. They are defined as wrapping around, and in debug mode, you'll catch it, and then in release mode, you can turn it on, but by default, it's turned off. Yes?
Is there already a natural interface to write parallel code for common graphics cards?
There's a surprising number of graphics libraries in Rust today. There's been a lot of push towards not using like OpenGL and kind of all that crazy stuff. I'm not the best person to talk about this. I know there's many others, but there are many projects that are like games written in Rust, OpenGL bindings written in Rust, new like GLFW written in Rust itself. I don't know a lot about graphics. Was that answering your question?
Yeah, I mean, kind of if there's something like CUDA for C++.
Oh, in that sense, running Rust directly on the GPU?
Yeah.
Oh, sorry. So that has been done in the past. There's not currently a majorly stable way to do that. We're in terms of a code generator, we're limited by mostly what LLVM does. So LLVM does have the ability to do that, and I've seen people write like little small kernels that actually run on the graphics card itself, but that was years ago before we even hit 1.0, and there's nothing stable in the compiler currently. Yes.
Just in this example here, you have the less and the greater.
Mm-hmm.
They're mutable when passed on to the parallel sort method. And what would happen if, let's say, this parallel qsort function would decide to push on this vector because it's mutable? And you're saying they're coming back magically because it's all the same array in the memory, but I could relocate that array, right?
This is actually something that I forgot to say, but this bracket here is actually not a vector. It's kind of terrible name now that I think about it, but this is actually a slice. So a slice in Rust is just a window into array, so there's actually no push operation on this. You can't actually push because this is not even a method. We have this, like, a mutable reference to a vector you can push on. A mutable reference to a slice just means you have some window where you can mutate the contents. You can kind of, like, in this case, we can sort them, we can swap them, all that fun stuff. All right. Oh, yes.
Does this slide to the double pipes?
Ah, yes, this is the syntax for closures. So if you had like bracket arg bracket that's like a closure that takes one argument, and then there's the expression the thing afterwards is just the body of the closure. It was also, there's a better example on the channel slide. This one. So you can see these double bars are saying there are no arguments to this closure, and then the curly braces are saying the body of this closure is the stuff inside there. The move is just a, don't worry about that.
When you explained the shared references, you said that the object that I give my, or the function that I give my object to will make a reference on, so kind of point to this vector.
Mm-hmm.
And now if I again share, I'm going to have kind of a long chain of this reference. Is this in any way kind of generating a long way to access my data?
It kind of depends what you're actually sharing. So if you pass around this vec pointer and like you're just passing around this ampersand vec of I32, you're actually just passing around the pointer value itself, so you're not creating more and more references. But if you pass around like ampersand vec of I32, then you are creating a reference chain. But it's one that you have to like explicitly opt into. And you probably won't be creating like ampersand. It probably just won't happen that often.
Recursive functions, like somehow.
Yes. There are also compiler limits where a lot of times you'll do that, except it's in a generic fact context, so it actually is infinite, and the compiler just chokes saying, "No, you can't. Sorry, I can't actually compile that." Yes.
Not sure if the question is too big for now, but the unsafe sections, can they make any guarantees for the rest of the program? Does unsafety not propagate up the hierarchy?
Right. So that's actually a big thing in Rust is that once you have unsafe code, it doesn't pollute. It doesn't go to the outside. Like it is unsafe, and the unsafety does pollute in a sense, in that the safety is dependent upon a lot of the code around it as well. But if you were to say that unsafe code propagates outwards, then that means essentially everything in Rust is unsafe, which would not be much benefit. So the real benefit comes from containing this. And there are some active research projects in terms of kind of defining what is unsafe, what are the actual invariants you need to do here, like what's the Rust memory model that you have to apply here, and then not only that, but also kind of verifying unsafe code. There's actually some small projects, I think maybe a big grant doing this actually, but it's trying to look at specifically the unsafe subset of Rust and trying to prove various things about it. So you could hand this analysis tool a bunch of this and say like, these are like, this piece of unsafe code is actually just safe in its entirety. If that makes sense. We can certainly talk a little bit more about this if you want to. Yes.
How good is the IDE support yet?
That's also a very good question. Unfortunately, I will say Idris was way better. Idris was really good. Like writing your program for you is not something that's going to happen in Rust, unfortunately. But the IDE support is kind of in progress and coming along. So like if you're kind of working in Vim or Emacs, kind of the bare bones works. I think IntelliJ is actually coming pretty good in terms of autocompletion. We've had this project called Racer in the past, which it works well. It's not perfect. But one of the major motivational factors of the incremental compilation story and kind of this major refactor of the compiler we're doing right now is that we're going to enable this sort of IDE support. So we have a lot of designs for the concept of this whole Rust language server, which is kind of a long-running daemon in which you feed code and you can just query it for things like, what are the autocompletions here? What are the methods here? What are the types here? And kind of happens over time. It's not implemented yet, so we'll kind of see this develop over time once incremental starts moving a little farther. But it's something that we had a survey at the beginning of this year, and the #1 thing that was requested was more IDE support. So we're going to see a lot more developments on that as the year goes on.
How is the core team financed at the moment? So how do you get money for this?
Right. So I think, from what I currently know, all full-time developers of Rust are currently paid by Mozilla, all within the Mozilla Research Organization. The core team itself, we don't have much financing for Rust in terms of like managing through a foundation or anything currently. It might happen eventually. But also the core team is not exclusively Mozilla right now. We have a couple members, for example, from Tilda or some independent contractors, and actually a guy working in Apple now, although he just started as a new employee. Yes.
For example, if I have a multi-threaded program, can I allocate memory locally? If I have a NUMA system with multiple sockets, for example? Is that done automatically? Because I mean, in C or C++, it's basically what it would do automatically if I allocate memory in the right thread, right?
Right. So I'm not super familiar with those kinds of architectures, but most of the time, whatever you would do in C and C++ is essentially what you do the same thing in Rust. So in terms of like bare metal abstractions, you can actually, there are two somewhat standard libraries in Rust. There's the major standard library, and then there's the component inside of it called libcore, which is actually just a subset of the standard library itself. And this is a subset which doesn't understand how to allocate, doesn't understand how to spawn threads. That's kind of like doing the most predictable thing you would expect from C. So you can drop down to that to not use any extra allocation, or like not use any extra fluff. And otherwise, it's just like when you allocate, like currently we default to jmalloc, but you can kind of swap that out to something else. But you would have control kind of, as long as L of n can express it, and as long as you can express it in the source language in C and C++, it would essentially be the same in Rust. That's not probably a great answer to your question, but that's what, but yeah. All right, so I also have two people here with me who also know a lot about Rust. So if you have any questions, just come find us afterwards and you can ask us anything. But otherwise, thanks so much for your time.